Hello, students. In today's lecture, we are going to learn about systems of particles and rotational motion, NCRT section 6.11 and example 6.12. This is disclaimer. Learning objective. By the end of this lecture, you will be able to understand the concept of analogy between rotational motion and translational motion, work done by a torque, instantaneous power, and rotational analog of Newton's second law. All right. So, in today's lecture, we will cover first dynamics of rotational motion about a fixed axis, then work done by a torque. Example 6.12. So, before starting, or we can say discussing the dynamics of rotational motion about a fixed axis, we will discuss analogy between rotational motion and translational motion. So here we will compare translational motion, or we can say straight line motion, with rotational motion, or we can say circular motion. Both follow similar laws of physics but with different quantities. We will understand the analogy using five main physical quantities. First, inertia. So in translational motion, inertia is represented by mass. This one. It tells us how much a body resists change in its linear motion. Whereas in rotational motion, inertia is represented by moment of inertia I. It tells us how much a body resists change in its rotational motion. Alright. Just like mass resists acceleration in a straight line, moment of inertia resists angular acceleration. Second is force and torque. So in linear motion, we apply a force F to move an object. So according to Newton's second law, F is equal to ma. But in rotational motion, we apply a torque tau to rotate an object. In rotational motion, tau equal to I alpha. Alright. So force makes objects move in a straight line, whereas torque makes an object rotate. Third is next is displacement. So in translational motion, displacement uh, x, or we can say dx, measured in meters, it shows how far the object has moved in a straight line. Whereas in rotational motion, displacement is theta or d theta, measured in radians. It shows how much the object has rotated. Alright. Next is we can say here linear displacement shows how far an object moved, whereas angular displacement shows how much it turned. Next is work. So in linear motion, or we can say translational motion, work is equal to force into displacement F dot dx. But in rotational motion, work is equal to torque into angular displacement. Linear work depends on force and distance, whereas rotational work depends on torque and angle. Here angle is theta. Alright. Next is simplification of components of forces involved in rotation about a fixed axis. So now when a body rotates about a fixed axis, so here uh, let's imagine a simple and common situation. So like a door. So we all open and close doors every day. Yes or no? But have you ever thought about how the door rotates? Yes or no? So when a body rotates about a fixed axis, so a fixed axis means the rotation is happening around a specific line. This one, axis of rotation. And that line does not move. This one. Like a hinge of a door. It stays fixed and the door rotates around it. Around this axis of rotation. So suppose first we can say push the door from its edges from the hinge. So in that case, what happens? The door opens. Yes or no? That is rotation because I am applying force perpendicular to the door at some specific distance from the hinge. This creates torque which causes rotation. So only the component of torque along the axis of rotation will cause rotation. So now uh, second force we can say here, some force don't cause rotation. Now suppose I push the door towards the hinge. So in that case, uh, what will happen? Tell me. The door won't open easily. Yes or no? It might shake a little, but it won't rotate because there is a no perpendicular distance from the axis. The torque is zero. So even though I am applying the force, it does not help in rotating the door. So components of the force that act parallel or along the axis of rotation, parallel or along the axis of rotation. So in that case, rotation don't help in axis of rotation don't help in rotation. So only the component of torque along the direction of fixed axis, like the hinge, helps in rotation. So torque components perpendicular to the axis of rotation, perpendicular to axis, only try to shift or bend the axis, but they don't cause motion. All right. So we can say here, to rotate something around a fixed axis, your force must create torque along that axis. Otherwise, no rotation. Any doubt? So, calculating torques on a rigid body. So, only those forces matter which are perpendicular to axis of rotation. Yes, because forces along the axis parallel to it do not produce torque about the axis. Forces parallel to axis will give torques perpendicular to axis and can be invoked. So we know tau equal to R into F. When R or F is along the same direction as the axis, their cross product becomes 0. Alright. So uh, think a door. This one. Think a door. You push the door straight into the hinge along the axis. Along the axis. Will it rotate? Yes or no? No. Because there is a no torque generated. But if you push the it perpendicularly, so it the uh, say at the handle here, that it easily rotate. So that force is axis, perpendicular to axis of rotation. So it creates torque. All right. Only the components of the position vector, only the components of the position vector that are perpendicular to axis of are important here, because if a part of object, a point on the door, is aligned along the axis, it won't help in rotating the object. So again, only perpendicular distance from the axis matter when calculating torque. So this is like a tau equal to R cross F, and if R is the parallel to the axis, cross product again becomes 0. So here the important point is this: use the forces and distance perpendicular to axis of rotation. Ignore anything along the axis, it does not help with torque. Alright. So for a door rotating around its hinge vertical axis. So imagine a door that rotates about its hinge. This one. The axis of rotation here is a vertical running through the line of the hinges. Now let's talk about what kind of force actually makes the door rotate. So uh, when you push the door horizontally perpendicular to the hinge axis, it creates an effective torque that rotates the door. Okay. So here what happens? It creates torque. This torque is what rotates the door, because the force lies in a plane that is perpendicular to the axis of rotation, which is the condition for generating torque. So only force that are perpendicular to axis, like a horizontal pushes are responsible for rotating the door. All right. Now imagine you try to push the door up, door up or down, like trying to lift or press the door vertically. So these forces are parallel to the axis of rotation. All right. So in that case, what happens? No rotation occurs. All right. These vertical forces do not create torque because they are aligned with the axis, not perpendicular. So we can ignore the such forces when analyzing rotational motion. So ignore it. All right. Work done by a torque. Now we will understand the work done by torque. Work done by a torque. So consider here a particle P on a rotating body. So look at here, figure 6.29. Uh, Specifying the angular position of a rigid body that rotates circular, that rotate along the circle path. So P particle P on a rotating body around fixed axis, or we can say Z axis in XY plane. XY plane. So the cross section of a rigid body rotating about a fixed axis or fixed Z axis perpendicular to the plane of the page, that is given as this one. So we have a particle P1 here. So the work done by a force F1 acting on the particle of a body rotating about a fixed axis. The particle having circular path with center C. This one. So arc P1 and P prime. This one. Uh, the area covered. The arc P1 and area covered by the arc P1 and P prime is ds1. ds1, and this is the displacement of the particle. So we know in rotational motion how we can calculate the work, that is applied torque into angular displacement. So here the displacement is ds1. So now uh, the angle work done by force F1, this one, which lie in the plane perpendicular to z axis in taking particle from P1 to P prime. The angle is phi 1, and with the applied force the angle is alpha 1. So you know in translational motion, or we can say in linear motion, what is work done? So it is force into displacement. So here dw1 is equal to f1, that is applied force into displacement, and the area covered by the arc is ds1. So f1 dot ds1, where ds1 is the small displacement. All right, I think you can relate this uh, that we already discussed in previous lectures in work energy power. F is work done is equal to force into displacement. Yes or no? So using dot product, we get dw1 is equal to f1 ds1 cos phi 1. You know, phi 1 is the angle between force and displacement. So when we solving this dot product, the answer is f1 ds1 cos phi 1. All right. Here phi 1 is the angle between force F1 and tangent at point P. So for small displacement ds1, because the here area covered by the arc P1 P1 prime is ds1. So the small displacement ds1 is equal to r1 d theta. R1 d theta. All right. So therefore dw1 is just put the value. We know dw1 is equal to f1 dot ds1. So solving the dot product, you will be get f1 ds1 cos theta, cos phi 1. Here phi 1 is 90 degree minus alpha 1. This is the perpendicular, na? Perpendicular. So whole angle is 90 degree. So 90 minus alpha 1. 90 minus alpha 1. This one cos 90 degree minus alpha 1. So it will be dw1 is equal to f1 r1 d theta cos 90 minus alpha is sin alpha. You know the formula, cos 90 minus theta is equal to sin theta. So here the angle is alpha 1. So cos 90 degree minus alpha 1 is equal to sin alpha 1. All right. Are you get it? Got it? So f1 r1 d theta sin alpha 1, where alpha 1 phi 1 is the angle between force f1 and radius vector op, op1, op1, this one. All right. So Rearranging the terms in work done by the force F. So it will be uh, dw1 is equal to r1 f1 sine alpha 1 d theta. So this is the force terms, and this is the angular displacement. So in terms of cross product, we know cross product A cross B is AB sine theta. So in terms of cross product, dw1 is given as r1 cross f1 d theta. Here r1 cross f1 is r1 f1 sine theta after solving the cross product. So this is the only mathematical terms. Now magnitude of the torque tau 1 acting on the particle is mode of tau 1. So that is r1 cross f1. Yes or no? So calculating this, dw1 is equal to tau 1 into d theta. So just put the value tau 1 and solve it, you will be get the magnitude. So this gives the small work done by the F1 in terms of torque that it produces. The important point here is this. So this is the small work done. Listen carefully. This is the small work done by the applying force F1. So what happens when the forces act is multiple, acting force is multiple. So if there are more than one forces acting on the body, in that case the work done by all of them can be added to give the total work done on the body, because we know work done is a scalar quantity, it has only magnitude, there is a no direction. So to calculate the work done by the more than one forces acting on the body, we can write uh, here dw is equal to r1 plus r2 plus tau 1 plus tau 2 plus tau 1. Here there is a more than one force into angular displacement d theta. Tau dw is equal to tau into d theta due to single force, but more than one force is the dw is tau 1 plus tau 2 plus tau and d theta. All right. Where tau 1, tau 2 and tau 1 are the magnitudes of the torques due to the forces F1, F2 and Fn. So tau is equal to tau 1 plus tau 2 plus tau n. So sum of all torques. So total work done in the rotating body from theta 1 to theta 2. So that from angular displacement, the initial position is theta 1 and after some time the displacement is changes, or we can say theta 1 to theta 2. So in that case, the total work done W is equal to integration theta 1 into theta 2 tau d theta. So when we comparing this work done in a linear, or we can say translational motion, we can say W is equal to F dot integration from x1 to x2 F dot dx. Yes or no? In translational motion, the formula to calculate the work done by applying a force, that is integration x1 to x2 limit and F dot dx. But in the rotational motion, or we can say in the dynamics of rotational motion, the formula of the work done W is equal to theta 1 to theta 2. This is the lower limit to upper limit. This is the displacement, angular displacement, and mode of tau into d theta. But in uh, translational motion, the limit is x1, x2. So this is the change displacement, linear displacement. Here the displacement is angular displacement. So I think now this is clear between angular, the work done by a torque and work done by a force in linear motion and in a rotational motion. All right. Instantaneous power. You know, instantaneous means at a particular instant. All right. Let's discuss. So here question arises, uh, what is power? So power means how fast work is done or energy is transferred. But instantaneous power is defined as the rate at which work is being done by a torque acting on a rotating object. Mathematically, P is equal to dW upon dt. This is for a whole time interval. All right. So now instantaneous power, we know dW is equal to tau d theta. So therefore instantaneous power is equal to dW upon dt. So just put the value of P. This one dW is equal to this one. So look at here. dW is equal to tau d theta and P is equal to dW upon dt. So just put the value of dW here. You will be get this one. And P is equal to mode of tau into omega. Here omega is the d theta upon dt, or we can say angular velocity of a rotating object. So this is the instantaneous power in terms of torque. All right. Rotational analog of Newton's second law. So uh, in linear motion, or we can say in translational motion, straight line motion, Newton's second law is force is equal to mass into acceleration. Here F, where F is equal to net force and M mass and A linear acceleration. So that tells us how a net force causes acceleration in a body. Now let's apply this idea to rotational motion. So in a perfectly rigid body, rate of increase of kinetic energy equals to the rate at which work is done on the body. So mathematically, rate of increase of kinetic energy is equal to rate at which work is done. So rate of kinetic energy dk upon dt and rate at which work is done dw upon dt. Here w is the work done on rotating body and k is the rotational kinetic energy of the body. I think this is clear because we already discussed the uh, rate of kinetic energy. So we know the kinetic energy of rotating body with moment of inertia I is k is equal to I omega square by 2. Yes or no? So the rate of increase of kinetic energy is, just put the value of k in differentiation form. You will be get dk upon dt is equal to uh, differentiation of I omega square by 2. So it will be dk upon dt is equal to I omega d omega upon dt. All right. So moment of inertia is taken as a constant. It means mass of the body does not change. So body remains rigid and also axis does not change its position with respect to body. So here dk upon dt is equal to I omega alpha. Here d omega upon dt is alpha. Angular acceleration of the rotating body. All right. So we know work done by a torque tau acting on the rotating body is dw is equal to tau d theta. Therefore, the rate at which work is done on the body is dw upon dt. So differentiate this one. You will be get tau d theta upon dt. Here tau is equal to mode of tau. So we can write dw upon dt is equal to tau omega. So equating rate of increase of kinetic energy and work done, we have dk upon dt is equal to dw upon dt. So dk upon dt is I omega alpha and dw upon dt is tau omega. This is in terms of kinetic energy and this is in terms of work. So we can say here from this relation I omega alpha is equal to tau omega. So omega omega cancel out. The remaining term is tau is equal to I alpha. This equation is analogous to force F is equal to ma in linear motion. So in Newton's second law, in linear motion, we know force is equal to mass into acceleration. But in rotational motion, tau equal to I alpha. I is moment of inertia in rotational motion, whereas in translational motion, m is mass. Alpha is angular acceleration in rotational motion, but in linear motion, acceleration A is linear acceleration. So I think tau is force in rotational motion and F is the force in linear motion. I think this is clear. This is the analogous to F is equal to ma. Therefore, when a rigid body rotates about a fixed axis, external torque tau produces an angular acceleration alpha. Alright. Example 6.12. A cord of negligible mass is bound round the rim of a flywheel of mass 20 kg. So we have a rim and the mass is 20 kg and radius 20 centimeter. A steady pull of 25 Newton is applied on the cord. So here a 25 Newton steady pull is applied. The flywheel is mounted on a horizontal axle with frictionless bearings. Okay. So you have to find out the A. Compute the angular acceleration of the wheel. It means alpha. Second, find the work done by the pull when 2 meter of the cord is unwound. C. Find also the kinetic energy of the wheel at this point and assume the wheel starts from the rest. So all three questions A, B, C are the formula based. Think about it. So given m is equal to mass is 20 kg, radius is 20 centimeter. So now we convert 20 centimeter in meter, it will be 0.2 meter. And applied force is 25 Newton. All right. So now flywheel is same as a disc. Yes or no? Flywheel is same as a disc. So moment of inertia of flywheel about its axis is I equal to 1 by 2 mr square. Moment of inertia, the formula is half mr square. So just put the value of m, the mass that is 20 kg and the radius 0.2 and squaring the radius, you will be get uh, 0.4 kg meter square. So this is the moment of inertia of flywheel about its axis. All right. Now angular acceleration. First we have to find out the compute the angular acceleration of the wheel. So angular acceleration alpha, we know the formula of the torque So that is tau equal to r cross f. So here r is the radius and f is the force. So just put the value. Here we have to find out the magnitude of the torque. So torque tau equal to the value of r is 25 into f is 0.2 into sine 90 degree, because this is the cross angle between r and f is 90 degree. So tau equal to what? 5 Newton meter. All right. So now we know torque can be written as in form of moment of inertia tau equal to I alpha, where moment of inertia I is 0.4 kg meter square. So just put the value, you will be get 5 is equal to 0.4 alpha. Here tau is equal to 5 Newton meter. So you can easily calculate the value of alpha. All right. So therefore angular acceleration alpha is 5 divided by 0.4, it will be 12.5 radian per second square. Yes or no? Now B, work done by the pull for unwinding 2 meter of the cord. So we know the formula of the work done, that is W is equal to force into displacement. Here the angle between force and L is 0 degree. The direction of force and displacement in same, so angle is 0. So W is equal to cos 0 1. So it will be FL, or we know the value of F and we know the value of L, that is 25 Newton into 2. So it will be 25 into 2 is equal to 50 joule. All right. Now kinetic energy of the wheel. So we know angular displacement is equal to length of unbound strings divided by radius of wheel. So length of unbound string is L divided by R. Theta is L divided by R. So length is 2 and R is 0.2. So when we solving this, we will get the value of theta, that is 10 radian. All right. So find the final angular velocity omega is we will calculate using the equation, that is omega square is equal to omega naught square plus 2 alpha theta. We already calculated, we already familiar with this formula. You know, in linear motion, v square is equal to u square plus 2as. But in rotational motion, angular velocity omega is, we can calculate omega square is equal to omega naught square plus 2 alpha theta, where omega naught is the initial angular velocity, that is 0 as a wheel starts from rest. This is given in this question. So using the values of alpha, theta and omega net, and put the value, give all the values in the uh, final angular velocity formula, you will get the answer. So omega square is equal to 0 plus, because omega naught is equal to 0. So 0 plus 2 into alpha value is 12.5 into the value of theta is 10. So it will be what? 12.5 into 2 into 10. So it will be 125 into 2. So when we solving this, you will be get 250. Omega square is equal to 250. All right. Now, therefore, rotational kinetic energy is K is equal to half I omega square. Here I is the moment of inertia. So just put the value of moment of inertia, that is 0.4, and omega square, that is 250. We already calculated. So just we calculate and you will be get 50 joule. So we can say rotational kinetic energy is 50 joule. So this proves that work done on the flywheel is converted into kinetic energy, and this confirming the work energy theorem. All right, work energy theorem. Uh, work done is equal to change in kinetic energy. Final kinetic energy minus initial kinetic. Summary. In rotational motion, moment of inertia is analogous to mass and torque is analogous to force in linear motion. Only torque components along the fixed axis cause rotation. And that is perpendicular here. Perpendicular components try to change the axis direction. Work done by the torque is dw is equal to tau d theta. And work done in rotation is w is equal to integration theta 1 to theta 2 tau d theta. And in linear translation motion, work done is equal to integration x1 to x2 f dot f dx, force into displacement. Instantaneous power in rotation, P is equal to tau omega. Rotational kinetic energy, K is equal to half I omega square. And rate of change of kinetic energy, dk upon dt is equal to I omega alpha. And rate of work done is d omega upon dw upon dt is equal to tau omega. So all these formulas are very important. And rotational analog of Newton's second law, tau is equal to I alpha. But in translation motion, we know F is equal to ma. Now we have some questions, practice questions, and this is homework for you. First, if a torque of 8 Newton meter acts on a wheel with moment of inertia 2 kg meter square, what is its angular acceleration? Second, calculate the work done when a torque of 6 Newton meter rotates a body through an angle of 4 radians. Third, what power is delivered by a torque of 10 Newton meter acting on a wheel rotating at 5 radian per second? Fourth, if the power delivered is 100 watt and angular velocity is 20 radian per second, what is the torque applied? Fifth one, if a wheel starts from rest and again attains angular velocity of 10 radian per second in 5 seconds, what is its angular acceleration? So all questions are formula based. All right. Thank you for your attention.